Okay, continuing on with the IC processing, we're going to look at something that's quite interesting. It's called atomic layer CVD, or atomic layer deposition. And basically it's chemical vapor deposition technique, but one layer at a time. It's used for high K gate dielectrics and metals for the gate conductors. The very interesting chemistry for this kind of technique. It's quite complicated. The surface is controlled by reactions that deposit one material in such a manner that the end groups, the atoms that are on the end of it, are receptive to the next layer material. So sometimes referred to as sequential surface chemistry. So there's precursors. These are gases of molecules that contain the materials to be deposited, and they're sequentially introduced into some type of a chamber. Each process itself is self-limiting, so only one atomic layer will grow of it, and then the reactor is purged, and purged of the whatever is off-gassing, I guess, at the time. The next molecule is introduced, and it's reacted with the surface, and then it will quit reacting, and then it's purged, and this process is repeated a number of times until the thickness of the layer is deposited. It's a low-temperature process, but dependent upon the material to be deposited. The growth rates are clearly proportional to the number of reaction cycles, but is usually relatively slow. It says limited to films less than 1,000 angstroms, but more likely less than a few hundred angstroms, or 100 angstroms. The following example is a process that shows the deposition of zirconium dioxide. It's deposited from zirconium chloride and water vapor. So these are the two precursors that are used in this process, and they're introduced to the chamber sequentially. So as we pointed out, it's going to be this example of the zirconium dioxide. It's used as a gate dielectric. As we saw previously, it had that high K characteristic. And basically this is the process, or more or less a schematic of the process, if you like. Here's a layer. You're introducing one of the precursors, H2O, OH groups form on the surface. Since there's now an oxygen sitting or hydrogen sitting on top and an oxygen bonded to the surface, it won't grow any further. The remaining reactants of that reaction are purged from the system, and then zirconium, was it chloride? Zirconium chloride, yes, is introduced, and then these guys react on the end of the, I guess there's an oxygen and hydrogen. The hydrogen is displaced, the zirconium sits there, and then the other, reactants of that reaction are purged from the system. So you build it up sort of one layer at a time. The only question I had in this kind of figure is that I didn't know where the chlorine went, but any event, I'll assume it's purged at this point in time. And at the end, if you do this sequentially, you'll end up with a layer of oxide, zirconium, oxide, zirconium, and effectively the structure looks like a crystal structure of zirconium dioxide. It looks a little bit like Tetris, the way these things are combined. And anyway, here's a nice little overview of the process for aluminum oxide, and that I think was basically showing each step in the chemical reactions that took place. Couldn't really find anything similar for zirconium dioxide. Anyway, for the atomic layer deposition, this is one of the benefits of the high K dielectric. I think this was a slide that came from an Intel site some time back, and basically it showed what previously what was happening for the silicon dioxide. The gate was getting gate dielectric was getting very thin, and more difficult to make defect free and have the same desirable characteristics if you made it any smaller. So the advantage of the high K is you can make it thicker and it'll have the same electrical properties. And here's a number of the high K dielectrics: aluminum dioxide, hafnium oxide, and zirconium dioxide. And there was the precursors for it. So that's where that expression sort of came from, physically thick and electrically thin. The opposite of deposition would be etching. This is a pattern is actually required for the formation of a device, and it's basically the etching that removes an unmasked portion of a layer. So etching was initially done in wet chemical baths, and basically it was an acid type of etch, as you might imagine, and it's still wet etching is still done, but much more likely you're going to find the process as being that of dry etching. So it's a predominant processing for IC fabrication, and it's basically basically reactants are extracted from a gas phase, and it's usually plasma assisted, which means that you create a plasma again with a neutral gas that's ionized. And some examples here are CF4 and O2 combined in a plasma can generate effective etching species for silicon dioxide or silicon nitride. So some of the advantages: flexibility to etch many different materials, certainly good for poly gates. It can be isotropic, which means it's sort of going in all directions, so it can etch in equally well in all directions, or perhaps more importantly, it can be anisotropic. In the event of a DRAM manufacturer, for example, you want to be able to etch very steep sidewalls to build capacitors, because as you know, a DRAM is a dynamic RAM and the charge is stored on a capacitor, and you don't want them to be big flat capacitors that would take up a lot of room. They're basically trench type capacitors. So this would be what that would tend to look like. These things were anisotropically etched in the silicon, so they're fairly deep and very steep sidewalls. And within that, you would then be able to deposit, let's say, an oxide and fill it with something, a conductor of some type, and then the outside side of the capacitor. So you can see if you're able to burrow those deep holes into the silicon, you're able to build a fairly small surface area, fairly small footprint capacitor, and it would have lots of capacitance associated with it. Lots being a relative term, of course. A number of different etching techniques. Plasma etching is one that's called plasma etching. One's called reactive ion etching and ion milling. And basically these range from something which is simply a chemical reaction on the surface where the reactants came from the plasma, or they're somewhat, in this case, ion milling. It's typically a physical or a process where it's sputtered. And somewhere in the middle you have the reactive ion etching, which is a combination of both chemical and physical process, removing materials from a surface. So reactive ion etching is by far the most popular form of dry etching used in manufacturing. And here's a picture of what one reaction chamber might look like, and in this particular case, sort of the schematic as well. Sort of shows you had an RF source, you had some wafers in here, and you have a big plasma down there, and it's reacting with the surface. And as you can see, it's under vacuum, and you put the gas in that you want to react under this RF excitation. You also have ion implantation. This is the introduction of ionized projectile atoms or molecules into target materials with enough energy to penetrate the surface. So it's sort of like a bullet going into a piece of wood. You've got an ion, you accelerate it through an electric field, and you implant it into the wafer. The source of the ions is usually a plasma. The ions are extracted from with either a DC or RF bias and accelerated onto the surface, and then they're you can control the energy in which they're going to the surface and basically the depth in which they're going to penetrate. Extensively used in IC fabrication, offers very sensitive control over many parameters during fabrication, and as I mentioned before, the depth of the atom's penetration is controlled by the accelerating potential. The dose is going to be a product of the beam current and the exposure time. That certainly makes sense. Here's a schematic, I guess, of an ion implanter, and you can sort of see you'd have a plasma source. You'd be exciting the particles, the ions. They go through a magnet. You get some kind of Lorentz force which curves them, and depending on their mass, they'll curve a different degree. So you can basically pick out the ion that you want, and then you accelerate that and raster scan it onto the surface of the wafer. Here's a website down here that you might want to find out a little bit more about the process of ion implantation. So here's an example of ion doping. You're implanting into a 1500 angstrom polysilicon layer, and it's sitting on a thin gate dielectric, which was, let's say, 20 angstroms thick. In this case, boron is implanted at 100 keV through a thin oxide layer, and this would be the result of the implantation. This would be as deposited, so you get this blue type of line here, and then this would be the annealed. So it went under some type of a temperature process, and it basically made the doping implantation slightly more uniform. Here's an example. If anyone is interested, they could come up and play with the implantation simulator. Another very fundamental process for IC manufacturing is photolithography. And this particular case, this shows a very simple example of a silicon wafer with a silicon dioxide layer grown on it, which we saw previously. And on top of this layer then would be a photoresist. So this is something which is, let's say, in a liquid phase. It's hardened slightly. It's spread over the entire wafer. And then just like the photography process, you put a mask in front of it. You expose it to UV radiation. And then what will happen is you're going to have a developed image. So what that means is the photoresist that was, let's say, exposed to the UV hardened. So this is a hardened polymer chain. So this is hardened, and the rest of it was washed away because it wasn't exposed to the light. So that's the same process that you'd expect with basic photolithography in a photographic process. So the UV hardened the photoresist, and where it was not hardened, it was washed away, and that gives you an opportunity then to etch the silicon dioxide. Now you're exposed to a layer below it, so you could basically put a hole in the silicon dioxide. Another process then would remove chemically remove the photoresist. So even though it was hardened, other chemicals can be introduced to basically undo the polymer chains, and you're able to wash away the resist, and you're left with an etched hole in the oxide. And if you want to see a nice little YouTube video of that, there's one down there, and there's probably lots more that you can find as well. At this point in time, we'll take another break.